have a lot to cover. In this session, we're going to talk about decorators as applied to functions or anything that is defined with a DEF. We're going to talk about class decorators, decorators that are applied to anything that starts with a class. We're going to talk about metaclasses. We're going to talk about an init subclass. We're going to talk about build class. We're going to talk about exec and eval. And so why don't we jump right in? I'll share my screen with you to get us started. It's often said that a decorator is a function that takes a function and returns a function. And while definitionally that might be somewhat interesting, it doesn't really lead me in the direction of why might I actually want to write a decorator or a higher order decorator? What use cases can this solve? What patterns might I see in my code that readily or make themselves readily solvable via decorators? Let's take a look. Well, there are a couple of distinct facts that we need to talk through before we can really appreciate decorators. Because it turns out that decorators in Python, or what we might call a decorator in Python, is not altogether that interesting of a thing. It's very much the case that what we call a decorator in Python is really just a syntactical transformation. And what's actually interesting about decorators is all of the stuff lurking behind them. For example, Python functions are defined at runtime. They're executed at runtime. Almost everything in Python is executable code, and even this def statement here is executable code. It is not the case that Python has some separate compile step that's going to build this function separate from the actual execution and creation of this function, although there is a parsing step that works through the body of the function. But the actual thing that brings this function into scope, that creates this thing that we call f, happens at runtime. This is why it is possible in Python for us to conditionally create functions. Here you can see we either randomly create f with x and y parameters or create f with just the x parameter. And as this module is executed, we determine which of these two we want to have in our module, which of these two we want to have in scope. Now, this is a fairly trivial example, and it's unlikely that this is something that would actually be useful in practice, in part because, well, for a random choice, sometimes you have two arguments, sometimes you want one argument. But you can imagine that if you are supporting multiple different platforms, Linux, Windows, and Mac, the way to go about doing some task may be substantially different on those three platforms. And you might want to provide people with one single unified interface for that functionality. If you wanted to do that, you could write one function where in the body of that function, it detected, am I on Windows? Am I on Linux? Am I on Mac? And then performed the platform-specific option. Or you could make use of platform.platform or platform.system to determine which system am I in. And you could say, if my system happens to be Linux, I do things one way. If my system happens to be another tool, I do things a slightly different way, or happens to be Windows or Mac, I do things slightly differently. Now, obviously, you'd probably want the signatures to look very similar. You probably wouldn't want them to be this distinct. But what you could do is take something that might otherwise happen at runtime and move it to module execution time. What's the advantage of that? Well, think about this. If the program starts on Linux, it's likely that 2 seconds into its runtime, it's still on Linux. I'm not sure I know of any ways to migrate a running program without terminating it from one operating system to another. I don't think that's even possible. And as a consequence, rather than performing a redundant runtime check every time I enter that body of that function, I can perform a single check on module execution to ensure that I create the right function, and that's used throughout the lifetime of this program. That way, I can have my cake and eat it too. I can have 3 options for how this program behaves that are determined when the program first starts without paying a redundant cost of every single time I run some function, figuring out which platform I'm in. Now, this also has some other implications. For example, we can directly create functions in Python. If we go into the types module and we look at types.function type, we can actually construct a function, and we can see what parts are needed to construct a function. Some code object. So the body of the function is definitely not evaluated when the function is first defined. Otherwise, why would we have that function at all? The function is oftentimes about deferring the evaluation of something. But the body of that function is parsed, and a code object containing the bytecode for that function is created. There are only a couple of interesting things that the parser actually does. One of those things is determine what scope variables come from. We'll see the implications of that later. Well, the function is really just a code object, some notion of what global scope, because the function could refer to some global variables it's working on, the name of the function, the default arguments for that function, and if that function happens to close over something, the closure. And so here you can see I recreated this function using types.function type. Probably not that useful in practice. I guess I could use it to rename things so that when I do help, the proper name shows up. But there's some other ways to do that. I can just assign directly into underscore name. There are further implications of this. For example, Python functions are data like any other, which means I can put Python functions into data structures as though they were any other sort of data. Strings, integers, functions can all be the elements of a list, the elements of a set, the keys or the values of a dictionary. Here you can see 3 pieces of code. Here I'm iterating not over the result of calling these functions, but over the functions themselves. Here I'm iterating over the result of calling these functions. And here, I'm iterating over some indirection to these functions, performing a lookup, finding the function I want, and then invoking that function. And you can think that there may be a reason why I might do either one of these options. For example, here, this may be the case where, the functions are relatively fast. I'll just run them all up front, and I'll show you what the output is. I don't need to invoke them. I don't need to defer the execution time. Here, it may be the case that at one point, I might break out of this loop. And when I break out of this loop, I don't want to execute. I don't want to evaluate the functions that I haven't visited yet, because then I'd just be wasting time, which would be very relevant if G and H happen to be particularly slow. Additionally, it may be the case that the loop body is the time when I have access to all the arguments that need to be passed into these functions. For example, if the result of F were then passed to G and then passed to H, well, I couldn't run them all up front here, but I could say, okay, execute F, and then execute G, and then execute H by putting it into a list. And here, obviously, you can see I can do some kind of switching mechanism. I could have some user input that determines which function is going to be called, or I can implement something very similar to a case switch in other programming languages. Note, when we define a function in Python, it needs to determine where the data that's going to be used in that function comes from. It needs to do scope determination. It needs to say, oh, Z, which is used in the sum of X, Y, and Z, comes from my local scope. It is a local variable. It's passed directly into G. X is not anywhere present in this definition. It's actually a global variable. And Y is neither a local variable nor a global variable. It is a variable that's in the enclosing environment. It's a variable that's in the closure. Now, if we take a look at the bytecode for G, we'll see something interesting. We'll see that X is determined to be a global variable, that Z is determined to be a local variable, but Python calls this a fast, an fast locals, and Y is determined to be a closure variable, but it calls it a deref here. See a little bit of the interesting terminology that the Python interpreter uses. But this is some function that involves 3 variables at 3 distinct scopes. This is something that the Python interpreter has to do when G is created, or rather when this code here is executed, and when it identifies that a variable as neither local scope nor global scope, it'll have to do some extra work behind the scenes in order to construct this closure.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.